This shape is absolutely insane. Not only can it drill square holes, but despite its sharp edge and sharp point, it can roll exactly as a sphere would. Let's talk about this and a few other interesting shapes as well, one of which can only truly exist in 4 dimensions, and another shape that is only made with cylinders, but you don't use pi to find its volume. Let's talk about this and more now. Speaking of interesting shapes that don't always fit the mold, if you've ever felt like a square peg trying to learn in a round hole's world, Brilliant.org is here to reshape your learning experience into something that fits just right. No awkward corners. CAD people, such as myself, are visual and spatial, and Brilliant is perfect for that kind of learning. It's also interactive, so you won't get bored and have an easy time internalizing what you're working with. I've been taking the Integral Calculus course, and I've particularly enjoyed the step-by-step process in learning where I can regularly test my knowledge and see explanations as needed. The courses are in small, manageable increments and are perfect for learning whenever you have time. Just 15 minutes a day can add up and give you awesome new skills and help you meet your goals. Advancing your skills in your career has never been easier as the world increases its demand for knowledgeable people. Most of all, this can help you become a better problem solver at work. There's something for everyone on Brilliant.org, whether you want to learn astronomy, computer science, data science, math, and more. This visually rich platform helps you learn how to think. For a full 30 days, you can learn for free by visiting Brilliant.org/jokoengineeringhelp. The first 200 will receive 20% off Brilliant's annual premium subscription. So take a look at this shape. You might think it looks a bit like an acorn, but it was actually studied by a German engineer named Franz Reuleaux. It was popularized by him, especially in his work called The Kinematics of Machines, published in 1875. Now, this is a shape of constant width, meaning that even though it's not round, it will roll like a sphere from the top to the bottom. Interestingly, although shapes of constant width have been known for centuries, they named this the Ruleaux Triangle because he popularized it. Now, Rouleaux triangles have a lot of interesting applications. They can be used in drilling square holes. They were based, I think, on the Wankel rotary as well. And also, you can roll them like a sphere. So if this constant width is confusing to you, let's take a look at how it's made. So in FreeCAD, let's go ahead and make a new part. And I'll start a new sketch here. Now I can choose my XZ, my XY, or my YZ plane. I'm going to go with XZ. And I can choose different pre-made shapes here. I'll click the drop down and select triangle. I also can toggle things with this toggle construction geometry button. And so I'll toggle that to blue. And I'll put down a blue triangle. And that, of course, means that we have geometry that is not driving. It's just there to help us with dimensioning and all that. So I'll give this line a horizontal. And I can choose a size. Maybe I'll go with 50 millimeters. And then I can toggle this yet again back to construction geometry. And I'll go with an arc. So I'll choose my arc button right here, create arc. I'll select one of the points of my triangle and start my arc on another point and finish my arc on the third point. And I'll do the same thing from here to here to there. And the same thing again. From there, I may need to re-add a constraint, so we'll go horizontal, just like that. And it looks like we're fully constrained. I think our sketcher is just throwing a little bit of an error here and not seeing that this is fully constrained. But this would be the cross-section of our constant width shape. So I'm going to delete my arc and delete my arc down here, or I also have the option of just drawing a line that'll be coincident on my arc. And I can choose this button up here, which is Trim Edge. And then I may have to simply re-add some constraints that were lost while trimming. Make sure that that's vertical. Looks like that it is. We'll go with the coincident. And there we are, fully constrained. So we'll close that. We'll simply do a revolve. And there is our constant width solid. So it's pretty darn simple. You just use an equilateral triangle and you've got it. Here's a shape that I hold in my hand that was discovered by two people independently. The first one was August Ferdinand Mobius, and the other one was Johann Benedict Listing. Mobius was a theoretical astronomer and mathematician. Listing studied a lot of 2D geometry and even coined the term topology, a term that we use quite often in 3D CAD. So they were pretty influential and quite interesting in my opinion. Now you look at the Mobius strip and you say, oh yeah, it's got an inside surface and an outside surface. But if I run my fingers, say, around one surface, you'll start to see that even when I keep my hand on the same surface, it ends up in the exact same place. So this has the same surface on the inside and the outside. It's all one surface, unlike a regular loop that we might think of. And this has a lot of interesting implications into the study of 3D geometry. Imagine a piece of paper, making it into a loop and cutting it in half. Then you have two loops. Boring! Now, imagine putting a twist in that paper and cutting it in half. Now you have a larger and more complex loop. You can cut it in half again and it becomes even more large, intertangled, and complex. And it can be cut in half an infinite number of times and remain a single loop. All of this complexity contained in a simple loop. How would you model this? Well, I'm going to cheat a little bit and use a script from Alibre. Let's get into it now. So on the Alibre website, there's an example script to make a Mobius strip autonomously, and I think it's pretty handy. So all I'm going to do is copy this code and put a link to this website in the description so you can find it yourself if you'd like to do this in Alibre. So here in the Alibre environment, I'll run over to Script. We're going to launch our console, and I'm simply going to paste in the code that I copied from the website. I'm going to make one change. We want our rotations, instead of 2, to be 0.5, right? We want it to go 180 degrees per revolution. With that being said, I'll run, and I think it's really fun to see the autonomous sketches and everything being made by a really cool script. Now, when we actually go to make this, we're going to have an error on our loft, right? This strip has a red error in it. And what's going on is the kernel doesn't know how to process a single loft that has a shared surface between the inside and the outside. Very understandable. I haven't tried this in all platforms, but I'm pretty sure if you try to do this in a single loft, every platform would probably error out in the same way, just by virtue of how these kernels work. So what I'll do instead is I'll go to Loft, and I'm going to grab just each sketch and do my own. And then when I get to my last sketch, I'm not going to try to project it to a new sketch, right? I'm just going to leave it just like that and do one extra face loft at the end. And that should finish up our Mobius strip. So again, very simple, made with automation. And of course, if you would like to do this in another platform and don't have a script for it, it would just be down to making planes and modeling it, slowly twisting through its sketches like this. All right, so if I want to do some final touches, I can add a fillet, maybe, 0.085 on one edge, and we'll go to the other edge, right? And we'll kind of make it a smooth transition so it kind of appears a little bit more like it's all one surface. That's probably good, right? So it's kind of smooth on the edges. That would be our Mobius strip. Well, we've talked about Mobius strips, but what happens when you put two Mobius strips together? Why, you get the Klein Bottle. Now, this is an interesting mathematical concept that was first discussed by Felix Klein in 1882. And if attaching two Mobius strips together sounds complicated, why, you're right. It can only exist in 4 dimensions, but we can come up with 3-dimensional approximations of what it looks like. This is a study of non-Euclidean geometry, meaning that you can go all the way around, and the inside and the outside are all the same surface without crossing edges. So Klein Bottle's inside surface is also its same outside surface, and it theoretically has a zero volume. But of course our three-dimensional models do have a volume because they're an approximation. So let's talk about how we would make a Klein Bottle in 3D. So in FreeCAD, let's make a new part. This time we'll go Part Design, create a sketch on the XZ plane, and I want to make this for 3D printing, so instead of arcs, I'm going to go with 45-ish degree angles. In fact, I'll grab an angle constraint over here. We're going to say 45. We're going to go horizontal, make sure that our line endpoints are horizontal. And I'm going to say E on my keyboard for equal, and that will make sure that those things are equal. I'll give a horizontal dimension to this line end and the origin. We'll say something like 10 millimeters. I'll go with a vertical dimension. Again, 10 millimeters. Vertical here, 10 millimeters, right? Good length. So where we're not constrained, we'll want to give this line a length here. From there to there. I say 45, maybe I'll say 25 instead. Just like that. Now, I should have enough freedom to make an arc just like that. We're going to go with a horizontal from this arc center to this arc end. We're going to give a radius, and I'll do a radius of about 50. I'll assume that my material thickness is about 3 millimeters, and I'll give another arc to about there. I'm going to say T on my keyboard for tangent. That will establish a tangent relationship between those arcs. We're going to go from this arc end to its center as a horizontal. And then I want to go the same distance as I did here, plus my material thickness. So we had a dimension of 10, and then I'm going to add 3 for my material thickness. I'm going to hit E on my keyboard for equal and make sure that these arcs have equal radii. And that gives us a completed Klein Bottle profile. Now I can shorten the length of my, or shorten the height of my Klein Bottle rather, of course by going with a smaller radius. Right? So I can go with 40 if I wish to do that. Next, in fact, I'll grab my multi-line tool. Just like that, create some multi-lines. I'll grab my parallel and choose parallel here and parallel there. Make a horizontal line closing off my profile there. And I'll go with a horizontal. Just like that. I want a thickness of 3, as said before, so I'll go with 3 here. And then I'll choose a vertical. And we'll go with 3 there. I also would like to, let's see, there's my arc center. Make a concentric arc here and a concentric arc there. I can say T for tangent, just like that. I'll get rid of that little coincident that automatically added itself and move that off. We're going to say horizontal. Give this a horizontal distance of 3. Much like that. Good. Then, horizontal line there. So I think our last degrees of freedom are how thick we want the floor on those. I'll flip this back to construction geometry and draw a line from here to there. And I can give that a distance of 3. Also, grab perpendicular, just like that. Again, our goal here. Oh, and it looks like a midpoint snap. I like that. We'll go with perpendicular there. Our goal here is to ensure somewhat constant floor thickness. We'll go with 3. Great. So that is probably the hardest part of making a Klein bottle. We'll close that. We'll add in a revolve here. And I'll choose this axis. Or I can specify here our Z axis. Looks like we've got a little error. Wire is not closed. And as you can tell, I'm missing that right there. So hopefully you caught that before I did. Let's make a little line there. Sometimes it's hard when you've got that axis in your view to remember to put a little line there. We'll go with revolve, and there we are. Next, we can see this part. So I want to start a sketch there. And I'll import this geometry there, and then I can create 2 circles and make them equal with the E key, right? So we're going to say equal, equal, and close. Now, my view is going to be a little bit crowded when I create this sketch. I'll want to see through this to the sketch that I've just made. So what I'll do is actually go with section view, just like that. Now, I can create an arc. I can use the horizontal constraint with the arc center and arc end to make sure that we end, right on vertical. I'll import, say, this circle, and we'll go with coincident from here to there, and then vertical, right? We're going to choose a little vertical from this point to the origin. And we're almost there. I'll click and drag this point right where I want it, right about there. And I'll add a line there. Select my line, select my arc, T for tangent, and I'll add an angle. I want my angle to be 45 degrees. So we're coming off at 45 degrees here. I want to give this a radius, and I'll go with something like 40, seems about right. And then I'll import this for the height. And I'm going to make an arc, right? We're going to make sure that our arc with this line is T for tangent. We also want to be coincident along this line with our arc center. And I want to add a vertical with the origin there. Oh, and we didn't like that. Well, because I think I accidentally grabbed a horizontal. So grab a vertical with the origin. Right there. Perfect. And we are fully constrained. I can change my constraint a little bit if I change my angle. So if I want this arc to have, a wider curve, which I think would be wise, I can take that down to 40 or 30 or so on. I also would like to take this back to, say, 30 because I want a straight section to cross that way. So I think we're going to be good there. I'll close. And this time we're going to choose sweep or additive pipe, as it's sometimes called. And I can select, say, this first sketch there. And we want to take it down our path, which I can go and select sketch 2 from my tree. Or I can select it in the graphics display, either way. We'll say OK. And that is our Klein bottle, except we have a big wall right here that we'll want to get rid of. So I'll grab a plane right there and say OK, and then start sketching on my plane. You can see my plane goes right with my path. So I can go to my model. I can hit the space bar to hide my datum plane from the tree. And then I can activate section view again, so I can see my origin and everything that I'm doing. So we're going to say just like that with a diameter of 20. Close, and now I can pocket. So I can kind of look from the other side here. I'll choose pocket. And maybe I can say, 25. And it looks like we eliminated our pocket and we haven't messed with anything else. So I like that. We're going to say OK to that. And that is a 3D printable Klein bottle. You may want to mind that there's going to be a little bit of support here and a little bit of support there. And if you alter your sweep path, you could probably get rid of that. But I think I'm happy with how we've done it here. I have a Hexisphericon. This is an intriguing and complex 3D object that when rolled, the entire outer surface is expressed by making contact with the floor that it's rolling on. This originated in the late 1960s when the cars were cool and everything was groovy. British carpenter Colin Roberts decided to make a Mobius strip without a hole out of wood, but he ended up making something known as a sphericon. This sphericon was something that meandered as it rolled along. In 1979, David Hirsch came up with something very similar, if not the same, I'm not quite sure, and ended up filing a patent on it in Israel. And then something called the wobbler duck was made with that shape, which was kind of a cool practical application. And from there, things got more complicated and eventually morphed into what we now call the Hexisphericon. Let's go through how to make it. So let's make a Hexisphericon in Alibre, and if you're in FreeCAD, you can do just the same thing that I'm doing. Follow the same steps. I've made Hexisphericons in both. It's a lot of fun. I'm going to choose the XY plane and create a reference sketch that's going to be a hexagon, and we'll apply that and close. We'll move this to up and down, and we'll give this a dimension here. I'll go with 3. You can make it whatever you'd like. And now I'll make a sketch on the XY plane again, and I'll start using this hexagon reference sketch. I think just having the reference sketch there sure makes a difference and makes it easier. Line, and I'll use the collinear constraint. No. So we're going to say project a sketch, and we'll project this as a reference figure with maintained association, and OK. And actually, now that I think about it, I could have just projected it as a regular figure. That's all right. We'll right-click, convert to regular. Next, we'll do a revolve, and we'll simply revolve it 180 degrees around this axis. There we go. I'll sketch on the face that I've just created. We'll project this, not the face rather, but just the edge with maintained association. I'll make 2 more lines. We can choose coincident here and make sure that this line is coincident with the origin. We'll also make sure that these are perpendicular, just like that. Deactivate, and we'll again do a revolve 180 degrees around. Our center plane will be this line here, and we'll reverse that, right? So that's our wobble when we go to roll things. And now we want to engage in our main rolling face, which will be over here. We'll do a rectangle. I'll choose a midpoint constraint on this line to the origin. Just like that. Now we're going to deactivate. We're going to do a revolve. We're going to select an axis here. Just like that, and we're still going 180 degrees. So, as you can tell, we're going to wobble, and then do our big roll over here. We also want to highlight this face, and we're going to want to create a rectangle in here that we can revolve 180 degrees. So we'll do that by 3 points, so we can get an angled rectangle. Once more, midpoint, collinear, and I'll also choose collinear. And that way we are fully constrained. We'll deactivate, revolve. We'll choose our axis, of course, here. Just like that. Now we'll want to activate a 2D sketch. I'll project this line with maintained association, just like that. We'll make 2 lines, and then I'll make this horizontal. Of course, you use the horizontal relation for that, and vertical. I'm just using some hotkeys, but of course you use the horizontal and vertical buttons up here. We'll revolve, we'll go to our axis, just like that. All right, last thing that we need to do is tie it all together. Just like that. We'll go with collinear here, collinear here, and coincident with the origin. And it looks like we have to be coincident with this point as well. We'll deactivate. We'll go revolve. There's our revolve axis. Just like that. So we have a Hexisphericon where when it rolls, the entire outer surface is expressed by touching the ground. Really, really cool. And that's how we make it in CAD. Well, those are just a few interesting shapes that I thought would be fun to go through, and I hope you feel inspired to make some interesting shapes of your own. We'll see you in the next one.